Hello everyone, welcome to GMAT Point. I'm Prakhar Jain and today we'll be studying about inequalities. While most of us understand what an equation is and how they work and what are the things that you can and cannot do with them, inequalities, while very similar, do have certain differences. There are certain things that you can do with an equation that you simply cannot do with an inequality. So let's get started. What is an inequality? An inequality is a mathematical statement that tells you whether a quantity is larger than or smaller than or sometimes even equal to another quantity. So for example, in an equation, you would have something like x equals 2. This tells me that x has the value 2. But in an inequality, you could have x is greater than 2. This doesn't give me the exact value of x. This tells me that x has some value and with just one constraint on it. This does not limit it to just one value. This still has an infinite number of values. So let's look at some inequality notations now. There are majorly four types of inequalities, which is what we'll be looking at now. The first one is greater than. This one basically tells you that the quantity on the left has some value that is larger than the quantity on the right, and it cannot even be equal to the value on the right. So like the previous example where we said x was greater than 2, the way to represent this is x is greater than 2 like so. The side that has the larger quantity gets the opening side to say of this notation. So this would tell me that x has a value larger than 2. What are some allowed values for this? You could have x equals 3, or you could have 2.1, 2.4, and so on. What are some not allowed values of x? You cannot have x equals 1 or 0 or 1.5, and you also cannot have x equal to 2. Because x has to be larger than 2, being equal to 2 does not satisfy that constraint for us. Let's look at the next one. The next one is lesser than. This is basically just the mirror of greater than. You could have something like, let's say, x is less than 2. In this case, the allowed values would be, for example, x equals 1 or 0 or 1.5 and so on. Values that won't be allowed would be x equals 3, 3.5 or 4 or 5 and so on. And you cannot have x equals 2 either, because the left hand side, which is x, has to be less than 2. So if you have x equal to 2, it's not less than 2 anymore. This is basically just the mirrored version of the greater than one. So let's move on to the next one. The next one is greater than or equal to. Now the way to think of this is that in greater than, we said that the value on the left cannot even be equal to the value on the right. In this case, it does allow an equality to the value on the right, and this is the notation for it. What this basically means is that in the case of allowed values, let's say in x plus 2, in x greater than 2, whatever your allowed values were, but this time x equal to 2 is actually allowed as well. So it adds one more value to the number of allowed values. It adds one more value to the set of allowed values. Similarly, in the case of x less than or equal to 2, the allowed values are simply the same as x less than 2, but again x equal to 2 is allowed. So we can see that in the four types of inequalities, two are just the mirror of each other, and then the remaining two are also just the mirror of each other. And even within those sets, the difference is minor. In one case, in the equal to case, the value on the right is actually one of the allowed values, and in the other case, it's not. Let's move on. Let's look at some examples now. First example, if x is greater than 2, does x equal to 1 satisfy the inequality? Pretty simple question. We have x greater than 2 and we have to check whether x equals to 1 satisfies it or not. We'll just simply put x equal to 1 and we'll be left with 1 greater than 2. We can see that this is not true. This is a false statement. So this does not satisfy the inequality. Let's look at the next one. If x is less than or equal to 4, does x equal to 4 satisfy the inequality? Well, we have seen that in the case of less than or equal to, if I was to simply put x equal to 4 here, I would get this. And as we saw before, less than or equal to allows for the quantity on the left to be equal to the quantity on the right, which means 4 equals 4 is a valid inequality. And this gives us that yes, it does satisfy the inequality. Now let's look at the third and the last example for now. Here we can see we have two inequalities. We have x greater than 0 but also less than or equal to 4. How many integer values of x are possible? Since we have two different inequalities within the one statement, it's better to just split them apart. So from the first half, we would get x is greater than 0. Now a quick side note, this says that 0 is less than x, which if you just simply flip it around, you would be left with x is greater than 0. So this is just the same inequality and we are pretty much allowed to do so. And on the second half, we have x is less than equal to 4. And one very important hint, this is a very common mistake people make, is they simply read the mathematical statement and skip over the rest of the question, especially when they're under time pressure. But one very important hint is that we are looking for integer values. So we don't actually need to consider all the fractions, all the decimals, or even all the irrational numbers. We simply have to look at the ones that are integers. In the first case, we have x greater than 0. What are the integer values that would be allowed? We would have x equals 1, 2, 3, 4, 5, 6 and so on. In the second case, we have x less than or equal to 4. First thing, x equals to 4 is indeed allowed. So we have x equals 4. And the remaining integer values have to be less than it. So we have 4, 3, 2, 1, 0, minus 1, minus 2 and so on. Now, because x has to satisfy both of these inequalities simultaneously, we can only look at values that are common between both of the inequalities. What I basically mean by that is that since x has to be within a certain range, it has to satisfy two inequalities at the same time. This means that only the values of x that satisfy both inequalities would actually also satisfy this entire statement. Now let's find out what these values are. We can see from 1 to 4 I have from 1 to 4 they satisfy the first inequality, and from 1 to 4 they also satisfy the second inequality. For the remaining numbers, we can see we are going higher up over here, whereas for this one we are going higher up in this direction, which means there are no more values that would be common between them. So again, counting up the number of values, we have 1, 2, 3 and 4. So there are 4 integer solutions to this statement over here. Now I want us to take this a step further. I want us to think of this in a number line format. This can be pretty useful for inequalities and we'll see this in some other questions as well. So let's quickly draw a number line. Now on the number line we have two constraints. One is 0 and another one is 4. So let's draw 0 and 4. The first inequality tells me that x must be greater than 0 and also that it cannot be equal to 0 either. So the way we draw this is we draw an empty circle on 0 because 0 itself is not allowed, and since the values to the right are allowed, we draw it like so. In the second one, we have x less than or equal to 4. So we draw a filled circle and the values to the left are allowed, so we draw it like so. Now, since we have to satisfy both inequalities at the same time, we can simply find the overlap between them and find the integer values that do satisfy this. We can see with the empty circle that 0 is not allowed. So we have 1, 2, 3 and the filled circle tells us that 4 is indeed allowed. So here again we can see there are 4 integer solutions. You can use either method. This method is usually helpful for situations like these. This method is usually helpful when you have multiple constraints. When you have constraints that might be, there might be some friction between those constraints. In this case, they are fairly straightforward, so we can simply use either method. Let's move on. Now we'll look at the differences between equations and inequalities. As I stated at the start of the video, there are certain things you can do with equations that you can also do with inequalities, but not all of them. The first one of those that you cannot do is simply change the signs. For example, in an equation, if you have x equals 2, it is completely valid to write minus x equals minus 2. You are simply multiplying both sides with minus 1, right? But let's look at what happens if this was an inequality. If I had x greater than 2 and I simply multiplied both sides with minus 1, I would have minus x greater than minus 2. Now, to check whether or not this is a valid operation, we can test it with an example. So let's say I put x equals to 3 to check this. If it satisfies both versions, that means the operation is valid. If it satisfies only one of them, that means the operation is invalid, right? So in this case, I have 3 greater than 2, which is valid. This is true, right? In the other one, if I put x equal to 3, I get minus 3 is greater than minus 2, which is not true. This means that my operation over here must have been an invalid operation. So this is proof here that you cannot simply multiply the two sides, or you cannot simply alter the signs on the two sides of an inequality the way you can do that for an equation. So what do we do? If I want to change the sign, what should I do? The way you do this is you simply switch the inequality for its complement. If you flip the inequality when you flip the signs, then there is no problem in doing so. Again, we'll test this with the same example. If I had x greater than 2, and if I was to multiply both sides with minus 1 and flip the inequality at the same time, I would have minus x less than minus 2. Again, testing it with x equals to 3, I am left with 3 greater than 2 on the left hand side, which is valid. On this side, I have minus 3 is less than minus 2, which is also valid. So this tells me that my operation right here is completely valid. So what is the rule about inequalities again? When we are switching their signs, is if you are multiplying either side with a negative number, you have to flip the inequality as well. As you can probably guess, it's not only true for minus 1. As long as it's a negative number, you have to flip the signs whenever you're multiplying both sides or even dividing both sides by a negative number. The flip always has to happen, otherwise your operation will end up being invalid and you've basically just made a mistake. Let's move on to the next mistake. Squaring both sides. So in the case of an equation, you can pretty much just square on both sides, right? If you have x equals 2, you can simply write x squared is equal 2 squared equals 4. This is completely valid in the case of an equation. But again, in an inequation, this might not be true. So for example, if I have the inequality x is less than minus 2, again, we'll just simply test it. If I was to square both sides, I would have x squared less than 4, or I'll explain it a bit more, which is 4, right? Now again, we'll test this. In this case, we'll test it with the number x equal to minus 3. So let's put x equal to minus 3. And on this side, we would have minus 3 is less than minus 2, which is valid. But on the right hand side, I now have minus 3 squared less than minus 2 squared, which gives me 9 is less than 4, which is invalid. This again tells me that my operation must have been invalid on its own. This is an invalid operation. Now what do we do in this case? In this case, it's not as hard and fast as it was in the case of altering signs. This is because not only the sign matters, but also the size of the number matters. So whenever you are squaring both the sides of an inequation, you always have to make sure that either both numbers are positive, or if one of them is negative, then your inequality must not be affected by the magnitude of that number. Both the absolute value and the sign must be kept in mind whenever you are squaring both sides. And this is not only for squares, this is true for all even exponents. And there is a reason behind it. So first of all, let's see what happens if it was an odd exponent. So if I had, let's say, I'll erase this first. Let's say if I had minus 3 less than minus 2 and I was to cube both sides without making any changes about the inequality, I would have minus 27 less than minus 8, which is true, which it did not work for an even exponent. This is because anytime you have an even exponent, even if you have negative numbers on both sides, what happens is the negatives get multiplied with themselves an even number of times and they start cancelling out. In the case of an odd exponent, that is not the case. So whenever you are introducing an odd exponent, you can simply ignore this rule. But whenever you are introducing an even exponent, you have to keep this in mind. Let's look at the last and the next rule. Let's look at the next rule and also the last rule for now, which is the reciprocal rule. Again, in an equation, if I have x equals 2, I can simply flip both sides as fractions and write this, and this is completely valid. This again is not true for an inequality. So for example, if I have x greater than y, I cannot simply write 1 by x equals 1 by y. Oh, sorry, I mean integrate is greater than 1 by y. Let's again test this with an example. Let's say if I was to put x equals to 3 and y equals to 2, then the left hand side becomes 3 is greater than 2 and the right hand side becomes 1 by 3 is greater than 1 by 2. This is valid, but this is invalid because 1 upon 3 is roughly 0.333 and so on. 1 by 2 is 0.5. So clearly this side is larger than this side and the inequality is invalid. Again, whenever you are doing reciprocals, you have to flip the inequality. This one is again just as hard and fast as the negative sign one. So quite simply, if I would have instead just written it as x greater than y, and then while taking the reciprocal on both sides, if I had written 1 by x less than 1 by y, this would have been valid. Again, we'll test this with the same example. Put x equals 3 and y equals 2. We have 3 greater than 2, which we saw was valid. On the right hand side, I have 1 by 3 less than 1 by 2, which is also valid. So if you just flip the signs whenever you're taking a reciprocal, you should be completely fine. There might be questions where you have both the reciprocal and the negatives. So in that case, you have to act accordingly. You have to combine both rules, and we'll see that in some examples as well. Let's move on. Let's look at the types of questions you can get in GMAT for inequalities. There's the obvious quant ones. I mean, this is a mathematical concept, so it will be there in quants. So it's a very prominent topic in quants. It might not have questions on its own, but it can be integrated into other topics questions. So we'll look at an example. If 3 is less than x and y is less than 5 and x and y are both equal integers, find the value of x plus y. This could very well be in a GMAT exam. It's the same difficulty level. So first of all, I'll write this as x greater than 3. You don't have to, it's just a preference where I like to have my variables on the left hand side. You can act according to your preference. I know x is greater than 3 and I know y is less than 5, and again, very crucial piece of information. They are both not only integers, they are equal integers. This means whatever values are allowed within this and whatever values are allowed within this constraint as well, x and y must be equal. There might be one or there might be more values. We'll see about that. In x greater than 3, the integer solutions I have are 4, 5, 6 and so on. In y less than 5, I have 4, 3, 2, 1 and so on. As we can see, there is only one common value between the two, which is y equals 4 and x equals 4. So that is the only possible solution, which is x equals y equals 4, which gives me x plus y equals 8. So that is our answer right there. Let's look at the second type of question you can get for inequalities. There is obviously the quant one which we saw, and the next one is data sufficiency. You can have math related data sufficiency questions, and this is a very prominent topic in data sufficiency because in an equation you get the exact value for a variable. In an inequality you don't. You have lesser information. And since data sufficiency questions are all about whether or not you have enough information, this is very common in DS. Almost everyone who takes the GMAT comes across at least one DS inequality based question. So let's look at an example one. But even before that, we'll look at what the structure of a DS problem looks like. In a DS problem, you basically ask the question. In this case, we have no information in the question itself. You may or may not have that based on the question itself. We are asked, is x greater than 2? And we have two statements. Basically, the two statements give you extra information that is not stated in the question itself. And you have to decide if, first option, if statement 1 alone provides you with the information needed to answer the question in the question itself. So if this was enough information and statement 2 alone was not enough information to answer the question, then you would have answered option A. Basically, the information you need. So in the question stated in any DS question, the question gives you part of the information. It does not give you all of the information. What you have to do is not actually get to the answer. You have to find out which one of these gives you the information to get to that answer, if any of them. or there might also be both of them. If statement 2 gave you all the information you need, but statement 1 did not, then your answer would be option B. If each of those statements gives you the information you need, so for example, if statement 1 alone without statement 2 was enough information, and also statement 2 alone was enough information, that's when you would answer option D. Each statement alone is sufficient. If both of the statements combined give you enough information, but neither of them alone gives it. So statement 2 alone, statement 1 alone is not enough information. Statement 2 alone is also not enough information, but together they give you enough information. That's when you would answer option C. And if they don't give you enough information, even when all of that or all of the statements are taken, that's when you answer option E. We'll look at this example to understand this in a bit more detail. So let's look at this through an example. The question in this case asks us, is x greater than 2? And statement 1 tells us that x squared is greater than 4. So I have x squared greater than 4. As we saw in the square rule, whenever you have an even exponent, you may or may not have had a negative number involved. If this was an equation, I would have the normal version, which would be x greater than 2. But if you look carefully, I could also have had x less than minus 2. For example, if x was minus 3, then x squared would be 9, which would indeed be greater than 4, right? So I can have both cases. This is all the information that statement 1 has given me, and I cannot conclusively say whether x is greater than 2. X equal to minus 3 also satisfies this inequality without satisfying this, whereas x equal to 3 satisfies this and does not, and also satisfies the question inequality. So this does not conclusively tell me whether x is greater than 2. So we can reject option A, and if you think about it, you can also reject option D. Option D says each statement alone is sufficient, and I know for a fact that at least one of them is not sufficient on their own, so I can reject option D. Okay, let's test our statement 2 now. It says x is greater than 0. Now this one's this one's much easier. This allows for the values, let's say x equal to 1, and also allows x equal to 3 since they are both greater than 0. But x equals to 1 does not satisfy the question inequality, whereas x equal to 3 does satisfy the question inequality. So statement 2 also does not conclusively tell me whether x is greater than 2 or less than 2. So I can now reject option B as well. The options I am left with now is whether or not the two statements together provide me with enough information. So let's see if the two statements together do or do not provide us with that information. I remember in x squared greater than 4, we had the two cases, x less than minus 2 and x greater than 2, right? Now, if I was to introduce statement 2 into this, I can see that this satisfies x greater than 0. This satisfies the inequality in statement 2, but this does not. X greater than 0 is not satisfied here. So if I was to put both the constraints from the two statements into the statement 1 constraint, then I can see this is my only possible answer. This is my only possible conclusion. Does this satisfy the inequality in the question? Yes, it does. It's the exact same inequality anyway. So both statements together are sufficient, but neither statement alone is sufficient. Option C would be our answer. Let's look at some more questions. Question 1 again. So before we start, in the questions, you will see there is a score level. So this question would be somewhere between 75 to 80 score level on a GMAT Quant sectional score scale. So for example, if this was to be in a GMAT Quant section, this is the level of question that someone with a 75 to 80 score should be able to solve. If you want to try these questions on yourself, then feel free to pause the video and try them. Here I have listed a time goal. Don't worry if you take longer than this, but the time goal is basically to tell you that if you are able to do this question in under a minute, then you should move on to harder questions, because at least in the terms of inequality, in the concept of inequality, you should move on to harder questions if you can do this in 1 minute. If you can't, it's fine. So just pause the video if you want. Let's get started. So question says, if x is greater than y, where x and y are both positive integers, then which of the following statements is true? X squared greater than y squared. Now we have x greater than y, and normally we would not be able to do x squared greater than y squared unless we knew that both of them were positive. But here I know that both of them are positive, so this is completely valid. We'll see through an example. 3 greater than 2, 3 and 2 are both positive integers, implies 9 is greater than 4, still valid. So option A is the correct answer. But we'll look at the other options anyways. Statement B, 1 by x is greater than 1 by y. This is a clear violation of the reciprocal rule. If we have x greater than y, so for example 3 greater than 2, if I had to take a reciprocal on both sides, I should have done this. I should have flipped the inequality, which they have not done in the option. Again, if I was to listen to option B over here, that would give me 1 by 3 greater than 1 by 2, which is invalid. So we can reject option B. Let's move on to option C. Let's check that. We have x plus y less than 2y. X plus y less than 2y. Now this here is going to be a good example of something that you normally do in equations that you can also do in an inequality. And that is moving added or subtracted terms from one side to another. In this case, you can simply move this over here to get x less than 2y minus y. This is an operation that you can do in equations that you can also do it in inequations. This gives me x less than y, which contradicts our question statement over here. So option C is also wrong. Now let's look at option D. X minus y is greater than x plus y. Okay, let's check that. X minus y greater than x plus y. If I cancel the x's out, I get minus y greater than y, which gives me, again, if y was a negative number, I could not have cancelled that out. I cannot divide with a negative number without flipping the signs. But because I know that y is a positive integer, I can cancel out y on both sides. This gives me minus 1 greater than 1, which is invalid, which means option D is also wrong. Test our last option, which is option E. We have xy less than y square. Again, normally I could not have cancelled out the options, cancelled out y on both sides if I did not know if it was positive or negative. In this case, I do. They are both positive integers, x and y. So I can simply cancel y out, get x less than y. I see that this is again contradictory to our question statement. So option E is also invalid. Our answer is option A. Let's look at the next question. This one is 80 to 83 score level. So if you were able to get the last one in under a minute, try and see if you can get this in 1 minute and 20 seconds or so. Again, if you can't get it, that's fine. You just need more practice. If you can, then you should try the next question in this video and try to get that one under the time goal as well. Feel free to pause the video. I'll just wait. Let's look at the question. If x and y are real numbers, is x greater than y? Okay, we are pretty much the only information we have is that x and y are real numbers, which if you think about it isn't all that information either. I don't know whether they're integers, I don't know whether they're positive or negative, I don't know if they're zero, they can be zero. So statement 1 says x squared is greater than y squared. This is again directly from the squares and square rooting rule. If I don't know whether they are positive or negative, I cannot say for sure if x is greater than y. Again, going back to the example we used, minus 3 squared is greater than minus 2 squared, but minus 3 is less than minus 2. And a counter example to that would be 3 squared is greater than 2 squared, but 3 is also greater than 2. So I just cannot tell whether x is greater than y or not. Statement 1 alone is not enough, and also each statement alone cannot have been enough. Let's look at the next option. Next statement, we have x plus y greater than 0. Okay, so we have x plus y greater than 0, which means I have x greater than minus y. This does not tell me if x is greater than y. Why? We'll look at an example. If let's say x was equal to 3 and y was equal to 2, I could have had 3 is greater than minus 2, which would give me that x is, I mean, in this case you have x greater than y as well. You have x greater than y in this case. But a counter example to this could be if you had x equals 1 and y equals 3. In this case, x is less than y, but x is still greater than minus y because 1 is greater than minus 3. So again, I cannot conclusively tell if x is greater than y simply going by statement 2. So option B is also rejected. Now let's test if I can get to the answer if I have enough information from the two statements combined. I have x squared greater than y squared and x plus y greater than 0. Let's start with the first statement. X squared greater than y squared. Again, doing the same operation, since I can move terms and as far as addition and subtraction are involved, I can write this as x squared minus y squared is greater than 0. For those of you who remember the identity, you would immediately spot that I can get x plus y times x minus y must also be greater than 0. In case you don't, you should remember this. It's a very useful identity. This is true for all real numbers. X squared minus y squared is the same as x plus y times x minus y. This is always true. If you knew this, great. If you don't, well, now you do. So, okay, so this is as far as we can get from statement 1. In statement 2, we can see that x plus y must be greater than 0. But even before that, let's look at this. So we have the product of two numbers, right? We have x plus y over here and we have x minus y over here. So we have two numbers and we are told that the product of these two numbers is greater than 0, which means it is positive. The only way you can get the product of two numbers to be positive is if either they are both positive or they are both negative. Right? If they're both positive, the product's positive. That's fairly straightforward. If they're both negative, the negatives cancel out and you get a positive answer. But if only one of them is positive and the other one is negative, then the product ends up being negative. So this tells us that both of them must be positive. And in statement 2, I am told for a fact that this is positive. So the only way statement 1 can be valid while statement 2 is also valid is if this was also positive. And the way we represent that with an inequality is that x minus y must be greater than 0, which means x must be greater than y. This means I can indeed answer the question with a yes or a no. It doesn't matter what you answer it with. In this case, it's a yes. The point is that both statements together are sufficient to tell me whether or not x is greater than y. Let's move on to the next question. This one is going to be an 84 to 87 score level. So we are getting into good, decent difficulty territory now. Try to get this one in a minute and 30 seconds. It ideally should not take you longer than that. If it does, it's fine. If it doesn't, even better. So feel free to pause the video. I'll wait. Okay, let's get started. So here we are given, you can see we have this statement over here. So we know that A is less than B, which in turn is less than 1 and A is greater than 0. So what do I know from this? I know that both A and B are less than 1. That's something I know. I also know that both A and B are positive. And I also know that A is less than B. So these are basically, this is basically just a breakdown of this statement right here, right? I've broken it down into 3 chunks. So let's look at our options. We are basically, okay, so there's a typo here. It's not about which of the following is true. It's about which one is greatest. So we have to find the largest of the values in the options. Anytime you have largest value questions like these, you basically just jump to the options. In options A and B, we can see that A must be less than B, which is something we got directly. So option A can simply be rejected because it's already less than another option. In questions like these, you can compare the options to see which one is greatest and then use that one as the test for the remaining options. So for example, right now, out of these two options, B is the greater one. Let's say if I was to come across an option that is greater than B, then option B cannot be my answer, right? But if in the remaining 3 options, I do not come across any option that is greater than B, then that means B must have been the greatest one. So basically what I'm trying to say is option B will be our threshold to check whether or not any of these options is the answer. Let's look at option C. So we have AB. Again, in another thing I want to mention is whenever you are dealing with questions like these, one very straightforward and simple way to check which one of them is greater is to simply find the difference between the two. If the difference is positive, then the first quantity must have been larger. If the difference is negative, then the second quantity must have been larger. Let's try it out. So let's write this out as B minus AB. I can simplify this into B times 1 minus A. Now again, I am at a place where I have two two numbers being multiplied. I know B is positive from here, so this is positive, and I also know that A is less than 1, which means 1 minus A. So if I have A less than 1, this tells me 1 minus A must be greater than 0, right? This means this is also positive, which means the entire product is positive, which means B must have been larger than AB, right? If I'm taking, let's say, 2 away from 3, then I'm left with 1. So if my remainder is positive, the first number must have been larger, which is true. 3 is larger than 2, right? So we can reject option C as well over here. Let's look at the next option, A squared. Now this is a different kind of question. If I was to write B minus A squared, there's not much of simplification I can do over here, but there is some other insights that I can use. So first thing, anytime you are squaring a number that has that is between 0 and 1, right? So it has a value less than 1. If x is less than 1 and greater than 0, then x squared will always be smaller than x. And again, if we can simply test this, since it is positive, I can cancel this out and I get x less than 1. Multiplying both sides, I get x squared less than x. So we can see the loop over here. Basically, anytime you square a number, you get an even smaller number. First thing, I know A is smaller than B from here. Now I'm squaring A as well. So I'm getting an even smaller number. So option D definitely cannot be the answer because A is less than B and A square is even smaller. Let's look at the last one. Now we have B and B squared. We could simply use the same logic. Since B is also between 0 and 1, I would simply have B squared less than B. But even if I was to use the difference method, I would have B minus B squared, which is B times 1 minus B. This is positive and B is less than 1, so this is also positive, similar to what we saw in option C. So this is positive, which means B is larger, so option E is rejected and our answer is option B over here. Let's move on to the fourth question. Now this one is an even more difficult question. Try to get this one in 2 minutes. It's on the 85 to 87 score level. So a lot of students will see something like this. Feel free to pause the video if you want to try the question. I'll wait for a second. Let's get started. So we can see we are given that x minus 1 over x plus 1 is greater than half. Then which of the following must be true? And we can see we are given various constraints on x. Basically, the question is just asking us what are the ranges of values for x for which this inequality holds itself true. So let's look at that. We have x minus 1 over x plus 1, which is greater than a half. Now, we need to be careful here because I am not told whether x is positive, whether x is negative, whether it's greater than 1, whether it's less than minus 1. I've not been told any of that. So I don't know if x minus 1 is positive or negative, and I don't know if x plus 1 is positive or negative. So now I need to consider all the possibilities. The way we normally do this is, in this case, if we put x minus 1 equal to 0, then x comes out to be 1. What this tells me that if x is greater than 1, then x minus 1 would be greater than 0, which we can see directly, right? And this also tells me that if x was less than 1, then x minus 1 would be less than 0. These are what we call critical points. These are the points where any function changes its sign. It goes from either positive to negative or negative to positive. This is why we call them critical points. So we can see from here we get the point x equals 1. From here, similarly, we would get the point x equals minus 1. So we'll draw a number line just for our reference. You don't have to. You get minus 1 here, you get 1 over here. And let's test this out. But as a general rule of thumb, because they must change signs, a number line is usually very helpful to draw. Now, at x greater than 1, both of these would be positive. So the whole function would be positive. At x, for x between minus 1 and 1, this would be negative and this would be positive. So overall the function would be negative, and again on left of minus 1, both are negative, so this would be positive. So I can immediately see that since this needs to be greater than a half, it needs to at least be positive, right? It needs to be greater than half, so it definitely needs to be greater than 0. So I can immediately tell that x cannot have values that are between minus 1 to 1. It simply cannot. So the only cases I am now left with are either x less than minus 1 or x greater than 1. Let's test these both out. We'll start with x greater than 1 first. If x is greater than 1, they are both positive, and because I can multiply both sides with positive numbers without any worry about the inequality, I can simply write this as 2 times x minus 1 is greater 2 times x minus 1 is greater than x plus 1, which gives me x is greater than 3. Now, we need to do a quick check anytime we get here, right? And the quick check is, this is a harsher constraint than this is. What I mean by that is, even though both of them have an infinite value of x's that would satisfy them, this one has lesser values. And the reason for that is that while this allows x equal to, this does not. This does not allow x equals to. And because I must satisfy both of these constraints for the case to be considered, right? So this allows me, for example, if this is x equal to 1, this allows me the values over here. But if this is x equals 3, the final result when I get to this assumption only allows me these values over here. So this was my assumption and this is my conclusion. I can only consider a value to be valid if both of them are valid at the same time. Both of them are valid in this region, which is based on the harsher constraint. Since that is what sets the bottleneck, that is what decides which values out of your assumption cannot be considered. So I already have x greater than 3 as a valid region. But I cannot simply answer this. If you look, option B and C both have x greater than 3. So if this is a valid region still, it would be answer option C. And if this is not, if as we check and it turns out, let's say it's not a valid case, then it would be answer B. Okay, so now we'll test the second inequality. At x is less than minus 1, this is a negative number. So when I multiply both sides with x plus 1, I must flip the inequality. And because when I'm multiplying with 2, it's still a positive number, I don't need to worry about that. So it only flips once. So I have 2 times x minus 1 is less than x plus 1, which gives me x is less than 3. So now I have these two constraints. In this case, the harsher constraint was my assumption constraint. So I must have x is less than minus 1. So our option is answer C, because this is a valid region and so is this. Now let's move on to the last question. This one is pretty much as hard as it gets in terms of questions where only inequalities are involved. There are harder questions that exist in GMAT, but they would probably be a mix of concepts with inequality or a mix of other concepts. This one you can spend more than 2 minutes. You can spend 2 minutes 20 seconds. You can spend 2 minutes and 30 seconds. The average time in the GMAT exam is meant to be 2 minutes per question, but that's an average. You can spend more time on a difficult question. Try to get this one in the time that I have stated over here for 2 minutes and 20 seconds. If you can't, again, don't worry about it. This is pretty much very close to 100 percentile scores. If you can, great. Maybe move on to a topic where you can't. I'll pause for a second and feel free to try this on your own. Okay, let's get started. Now I am given this statement over here. As you can see, the statements are getting longer with the questions. So I have been given the first piece of information I have is x is less than 0 and is greater than minus 1. So it is a negative number with a magnitude less than 1. Next one I have been given is y is a positive number with magnitude less than 1. And the next piece of information I have is z is greater than 1. So I know that y and z are positive. Z has a value greater than 1, y lies between 0 and 1, and x is negative with magnitude between 0 and 1. Okay, now let's look at the question. Which of the following is the greatest? Again, we'll use the same approach. Whenever you have to test options for which one of them is the greatest, you simply subtract one from the other. You check whether the difference is positive or negative, and you make your conclusion. So we'll subtract option B from option A. We have x, y plus z minus x, z plus y. If I was to take z common from these two, I would be left with z times 1 minus x. And if I was to take minus y common from these two, I would be left with this. I can now take my 1 minus x out of these two, and I would be left with g minus y times 1 minus x. Now let's look at this product. For the first term, it is z minus y. I know z is greater than 1 and y is less than 1. So as a result of these two combined, I have z greater than y, which means this is positive. Now for the second factor, I have 1 minus x. I have 1 minus a negative number. So negative is positive, which means this is also a positive number. So the difference is positive. This means the number which I was subtracting from must have been the greater one. So my answer between option A and B is option A. So I can simply reject option B. Let's move on to the next option and test that. I now have x, y and z. Now, there are two methods for this. There is obviously the subtraction method, but in this case, we pretty much have a much easier method, which is to actually compare the values. You can simply estimate them, right? So if you have x, y plus z, and you have x, y, z. So first of all, we can see this is positive, and this is negative. So the total sum is negative. In this case, you have a large positive number because this is greater than 1. And you have a negative and a positive, but two numbers that have magnitude less than 1 being multiplied. Anytime you have two numbers that are less than 1 that are being multiplied, the product will be less than both of them. So for example, if x was, let's say, 0.25, we're going to assume it's positive just for the example's sake. And if y was 0.4, then their product would be 0.1, which is less than both of them. So if I was to now multiply the negative value of x, which is less than 1, and the positive value of y, which is also less than 1, the product will be smaller than both of them and will be a negative number between 0 and 1, and also in terms of absolute value smaller than x. This means I have a large positive number and a small negative number, so I am left with an overall positive, and since this is negative, I can reject this as being one of the greatest options. The other method obviously would have been to simply subtract the two. I would have xy plus z minus xyz. If I take xy common out of these two terms over here, I would have xy times 1 minus z plus z. So this would be a negative number, and this would also be a negative number since z is greater than 1. So this is an overall positive. Z we know is positive, so the entire thing is positive, which means this must have been the greater term, so I can reject option C again. Let's move on to option D. We have xy plus yz plus zx. Again, we'll simply subtract it from option A. Xy plus z minus xy plus yz plus zx. Xy simply cancels out. If I was to take z common out of all of these, I would be left with z times 1 minus y minus x, which is z times 1 minus x plus y. Okay, so we are at a product again. We know this is positive, right? Now this is one of those cases where you can't tell for sure if this is like what the exact value of this will be, what the range of it will be. But you can still tell whether it is positive or negative. And the way you do that is, okay, so let's say I was to try and make this whole number negative, right? The way I would do that is, this is obviously positive, so I want to minimize the stuff inside the square brackets. If I want to minimize the stuff inside the square brackets and I am subtracting something from 1, if I maximize this, then I am taking the most amount of stuff away from 1, which means I am minimizing the square brackets, which means I am minimizing the whole number. So let's try and maximize x plus y. The way I can minimize x plus y is, I know y is positive, so I will give it as big a value as it can. I know it can't be 1, but just for argument's sake, we'll assume it's 1 for now. So let's say y was 1, right? X, again, since x is a negative number, I would try to minimize it I would try to maximize it in terms of absolute value. I would minimize it. In terms of overall value, I would maximize it. So I am taking as little stuff away from y as possible. That would be 0. If it was minus 1, then I am taking more stuff away from y, right? Then it would not make it the worst case scenario for us. So I would take x equal to 0. So x plus y, the maximum value would be 1. Again, remember that it actually cannot be 1 it's going to be somewhere less than 1. So the worst case, it will be 0.99 and so on, right? Worst case, it's still less than 1, which means 1 minus whatever this is still going to be a positive number. It could be very small, but it will still be positive, which means the overall number is positive. So I can now reject option D as well. Now let's move on to the last option. Option E, we have yz plus x. Again, simply subtract it. Xy plus z minus yz plus x. I'll take x common out of these two. I would be left with x times y minus 1, and then z common out of these two, or rather minus z. So I am left with y minus 1 again. This leaves me with x minus z times y minus 1. I know y is a number less than 1 from here, so this is going to be negative. And I know x is negative and z is positive, so this is also going to be negative. So the overall product will be positive, which means this is greater and option E is wrong. Our answer is option A. Now, I can understand that we have gone over varying levels of difficulty fairly quickly, but don't worry about it if you didn't get all of them under your time goal. It's been stated as a goal for a reason. If you're not already there, that's fine. It's a goal for a reason. You're meant to slowly make your way there. Thank you for watching. This was Inequalities by Prakhar Jain and by the GMAT Point team. Please like, share and subscribe. And if you want to get to more informative content like this, there will be links in the description. We have a visual library. We have hundreds of practice questions that you can use for your own preparation. Thank you.